Hello, today we are going to talk about the polylogarithm, which is a very important special function because it is a lot related with the Riemann zeta function. So actually the polylogarithm is a generalization of the Riemann zeta function. So we are going to define the polylogarithm as a Li sub s of z equals to the sum from n equals 1 to infinity of z to the n over n to the s. Okay? If we remember the definition also of the Riemann zeta function, we know that this is the sum from n equals 1 to infinity of 1 over n to the s. So we can easily notice that if we take Li sub s of 1, well, this is equal to the Riemann zeta function, because if we plug 1 here, well, we are going to get exactly this expression that corresponds to the Riemann zeta function. Okay, so in this video we want to prove some fundamental relations regarding the polylogarithms. First of all, we want to start with the derivative. What happens if we take the derivative with respect to z of the polylogarithm of the derivative of the polylogarithm? Well, that is going to be the sum from n equals 1 to infinity of the derivative with respect to z of z to the n over n to the s, which is going to be, well, the sum from n equals 1 to infinity of m times z to the n minus 1 over n to the s, and this is, well, the sum from n equals 1 to infinity of z to the n minus 1 over n to the s minus 1. So here we have our first important relation, which is the derivative with respect to z of a general polylogarithm. Well, it's going to be the sum from n equals 1 to infinity of z to the n minus 1 over n to the s minus 1. This is the rule for the derivative. We notice that, well, we have here something very curious, that is, well, to take the derivative we just need to subtract 1 to the exponents of the terms in the definition of the polylogarithm. Okay, so just subtract 1 and you get the derivative. Okay, we can see this expression in another way. We can rewrite this formula as this: the sum from n equals 1 to infinity of, well, 1 over z times z to the n over n to the s minus 1. We can take this z out of the sum because, well, it doesn't have to do anything with n. And this is going to be 1 over z times the sum from n equals 1 to infinity of z to the n over n to the s minus 1. And it's easy to notice that, well, what we have here is actually Li s minus 1 of z. Okay, so we got a kind of like a recursive relation for the derivative. We get that the derivative with respect to z of Li of z s is equal to 1 over z times, well, Li sub s minus 1 of z. So this is the second important relation that we find. So what happens if, for example, we take the integral on both sides of this equation? Well, let's say, for example, that we'll rename this equation by switching x for z, actually z for x. Well, we are going to get that the derivative with respect to x of Li s of x is going to be equal to 1 over x times Li s minus 1 of x. So taking the integral on both sides, well, let's rewrite it. We are going to get that the integral from 0 to z of the derivative with respect to x of Li sub s of x dx equals the integral from 0 to z or 1 over x Li sub s minus 1 of x dx. Well, we have here this equation, but let's notice here that we can use the fundamental theorem of calculus to easily notice that this is going to be, well, just Li sub s of z equals the integral from 0 to z of 1 over x Li sub s minus 1 of x dx. And this is the third important relation that we can find for polylogarithms. It's a recursive integral relation, and we have another here, another derivative recursive relation. Okay, so now we have just found 3 important formulas regarding polylogarithms. Okay, so now what we want to do is to establish, well, to determine some different cases, important cases regarding polylogarithms. For example, let's say the case when s is equal to 0. Okay, what happens if L is equal to 0? We need to calculate Li sub 0 of z. So using the definition, this is going to be, well, the sum from n equals 1 to infinity of z to the n over n to the 0 power, which is 1, which is just z to the n. So we know that this is very similar to the geometric series, but to use that, we need to establish that, well, the absolute value of n needs to be less than 1. Okay, so this formula that we are going to show now is only valid if the absolute value of z is less than 1, or the modulus of z, because you need to know that for polylogarithms we can use complex numbers. So in general, polylogarithms are complex functions, so z can be a complex number. Okay, so if we assume that the modulus of z is less than 1, and remember that the sum from n equals 0 to infinity of r to the n is equal to 1 over 1 minus r, and if we develop this expression, well, if we substitute n equals 0, we are going to get 1 plus the sum from n equals 1 to infinity of r to the n equals to 1 over 1 minus r. And we get that the sum from n equals 1 to infinity is equal to 1 over 1 minus r minus 1, but that 1 we can rewrite it as 1 minus r over 1 minus r, to get that this is r over 1 minus r. So this is the sum from n equals 1 to infinity of r to the n, which is actually the same, almost the same that we have here. We just need to rename r with z. So to get the next Li sub 0 of z is going to be, well, z over 1 minus z, where the modulus of z is less than 1. So this is the case where s is equal to 0. Okay, now let's jump to the case where s is equal to 1. Well, in that case, well, what happens if we use the definition? Well, Li sub 1 of z is going to be equals to the sum from n equals 1 to infinity of, well, z to the n over n. Okay, now, well, yeah, it seems to be pretty easy, but there's actually some other way to express L sub 1 of z that will be also very useful. Okay, but for now we need to recall the Taylor series expansion definition for the function natural log of 1 plus z, which is, that is going to be the sum from n equals 1 to infinity of negative 1 to the n minus 1 times z to the n over n. Look, we have something very similar, okay, but not exactly the same. So what happens, for example, if we take the natural log of 1 minus z? Well, we can just switch z for minus z in this expression and see what happens. This is going to be the sum from n equals 1 to infinity of negative 1 to the n minus 1 times negative z to the n over n. and this is going to be the sum from n equals 1 to infinity of -1 to the n minus 1. And if we take out of -1 from here, which is going to be raised to the n power, and then sum the powers of the negative ones that we have here, well, we are going to get, this is going to be 2n minus 1, okay, times z to the n over n. And let's notice here that we are raising -1 to an odd power. 2n minus 1 for all n is going to be always an odd number. That means that we are going to raise -1 to an odd number, which is always going to be, well, -1, that we can take out from the sum to establish that this is going to be equal to negative the sum from n equals 1 to infinity of z to the n over n, okay? And this definition, we know it. This is negative Li1 of z. So Li1 of z for the definition of the polylogarithms. So what we can say then is that Li sub 1 of z is equal to negative the natural log of 1 minus z, okay? This is equal to this. So this is what we get in the case where s is equal to 1. And very special is the case where s is equal to 2, okay? Where s is equal to 2, we are going to name this as the Dilogarithm, okay? Li sub 2 of z. What happens? Well, we are going to start by a definition that is different from the original definition. We're going to establish that the Dilogarithm is going to be equal to negative the integral from 0 to z of the natural log of 1 minus u over u du, okay? But let's look that, well, the expression negative natural log of 1 minus u is actually, well, by this definition that we proved, is going to be Li sub 1 of u. So this is going to be equal to negative the integral from 0 to z of Li sub 1 of u over u du. Okay, but now using the other definition that we have for Li sub 1 of u, this is going to be equal to negative, actually no, there is no a negative sign, because this is equal to this, so there is a plus, okay? So using the definition, this is going to be the integral from 0 to z of the sum from n equals 1 to infinity of u to the n over n, okay? But we have a u here, so that u is going to be, well, here, but we can rewrite this as u to the n minus 1 times du, okay? So we are going to assume that this converge, because actually I forgot to mention that also this definition needs to hold that the modulus of z is less than 1, okay? So switching the summation with the integral, this is going to be equal to the sum from n equals 1 to infinity of the integral from 0 to z of u to the n minus 1 over n du. And this is equal to, well, taking the integral, this is going to be the sum from n equals 1 to infinity of u to the n over n times n, but this is going to be n squared, from 0 to z, equal to the sum from n equals 1 to infinity of z to the n over n squared. And you can easily notice that this matches with the original definition of the Dilogarithm based on the main formula that we showed at the beginning, this one. Well, if we take s equal to 2, well, we get this expression that we have here. So with that, we have the proof for this equation over here. Negative the integral from 0 to c of the natural log of 1 minus u over u du. Okay, so now we have 3 special cases of the polylogarithms. We have, well, proved some very important relations regarding polylogarithms. Remember, this is going to be a very important special function. Looking at, well, it is very related with the Riemann zeta function. Okay, so now we have made a quick review on the fundamentals of polylogarithms. Feel free to comment if you have any question or any doubt regarding these processes.